what if I told you there's a chemical recipe that, on one hand, is responsible for feeding billions of people, but on the other, holds the key to incredible destructive power? Well, there is. And this is the story of a chemical puzzle that literally changed our world. Our story starts right here, with this absolutely catastrophic event. On August 4, 2020, a massive blast, basically a small earthquake, just ripped through the city of Beirut. The cause? The unsafe storage of 2,750 tons of a chemical called ammonium nitrate. So here's the big question. What on earth could possibly link a chemical powerful enough to do that to the food on your dinner plate? It sounds like a crazy connection, right? But stick with me, because it's one of the most important stories in modern chemistry. And the answer, it all comes down to one chemical: ammonia. Yeah, that explosive stuff. Ammonium nitrate is made from ammonia. But its main job, by far, isn't about destruction. It's actually about creation. It's the essential ingredient for the fertilizers that our crops need to grow. And to make all that fertilizer, well, you need an unbelievable amount of ammonia.
You know, ammonia is a true workhorse in the chemical world. Its biggest gig, something like 80% of it, is making fertilizer. Without it, we'd have no way to grow enough food for everyone. But it doesn't stop there. It's also a key building block for everything from plastics and fabrics to the cleaner you use in your kitchen. It's easily one of the most important chemicals we make.
Okay, so we've established we need a lot of ammonia. The problem? Making it is tricky. It's not simple at all. In fact, it took a real stroke of genius to figure out how to do it on a massive scale. That solution is called the Haber process. And honestly, it's a masterpiece of chemical engineering.
So here's the crazy thing. The air all around us right now is almost 80% nitrogen. It's everywhere. But it's super stable, kind of lazy. It doesn't like to react with anything, which means plants just can't use it. The big challenge then is to somehow grab that lazy nitrogen out of the air and force it to react with hydrogen. But this is where things get really, really interesting. See, making ammonia isn't like baking a cake where you mix the ingredients and poof, you're done. Nope, this reaction is a two-way street, and that's where the real puzzle begins. It's all because of something called a reversible reaction.
So what the heck is a reversible reaction? Think of it this way. As fast as you're making your product, in this case ammonia, the product is, well, it's unmaking itself. It's breaking back down into the very ingredients you started with. And this is all happening at the exact same time. It's a constant chemical tug-of-war. And this is a perfect picture of that chemical tug-of-war. You've got the forward reaction, where nitrogen and hydrogen team up to make ammonia. But look, at the very same time, you have the backward reaction, where ammonia decides, nah, I'm out, and breaks apart again. It's all happening at once, inside the same container.
And in chemistry, we have a special symbol for this whole process. It's that double arrow right there. See it? That's your big signal that you're looking at a reversible reaction. It's going left to right and right to left. Our job? Figure out how to rig the game so the forward reaction wins. So, if the reaction is constantly fighting itself, how do you win? How do you come out on top? This is the central puzzle we have to solve. And it's not just about getting a high yield of ammonia. You have to make it fast enough, and you have to do it cheap enough for it to actually be useful.
Okay, this graph right here, this is our secret weapon. It might look a little complicated, but it's basically a cheat sheet for solving our puzzle. On the side, you've got yield. That's just how much ammonia we get. Along the bottom, temperature. And each of those colored lines, that's a different pressure. This thing tells us everything we need to know.
All right, let's tackle pressure first. If you look at the graph, you can see the lines for higher pressures are way up at the top. That means you get a higher yield, more ammonia. Awesome, right? Well, there's a catch. Creating and holding that much pressure costs a fortune. We're talking massive electricity bills and super expensive heavy-duty equipment. Okay, now for temperature. Follow any one of those pressure lines. You'll notice that the yield gets better and better as things get colder. Lower temp, more ammonia. Perfect, except nope. The other catch is that when it's cold, the reaction slows way down. Like it becomes glacially slow. So slow that it's useless for making anything on an industrial scale. And this is the most important idea to grasp. In the real world, industrial chemistry isn't about getting a perfect 100% yield in a textbook. It's about finding the sweet spot. It's a compromise.
The real genius here is finding that perfect balance between getting enough product, getting it fast, and not going broke while you do it.
So what is that magic recipe? What is the compromise that chemists and engineers finally landed on? Let's take a look at the actual conditions that make the Haber process work all over the world every single day.
First up, temperature. They settled on 450 degrees Celsius. Now, if you look back at our graph, you know that's not the best for yield, is it? But it's the Goldilocks temperature. It's hot enough to make the reaction happen at a really good, practical speed.
Next, pressure. They used 250 atmospheres. Again, not the absolute highest pressure you could possibly use, but it's high enough to give a decent yield without making the electricity bill go completely through the roof. It's that economic sweet spot we were talking about.
But there's one last piece of the puzzle, the real secret weapon, an iron catalyst. Now, a catalyst is amazing. It doesn't actually give you more ammonia in the end. It doesn't change the yield. But what it does is speed up the reaction, like a lot. It's what makes that 450-degree temperature economically viable. Without this catalyst, the whole compromise would just fall apart.
And boom, here it is, the whole shebang, all laid out. You take nitrogen from the air and hydrogen from crude oil. You pump them into the reactor. You hit them with those carefully chosen compromise conditions, that perfect temperature, that sweet spot pressure, and that all-important iron catalyst. And out the other side comes ammonia. It is just an incredibly elegant solution to a huge, huge problem.
Okay, so the Haber process is the big one, the most famous reversible reaction. But this whole idea is everywhere in chemistry. So I've got a challenge for you. Look at these pretty blue crystals. Using everything you now know about reversible reactions, what do you think is going to happen when you heat them?
Think about it. Heating is just adding energy, right? It's going to push the reaction in one direction. But what if you were to add water back to whatever's left?
Could this also be one of those two-way streets? I'll let you figure that one out.
Thanks for joining me.